As I told you, we have a system, so this system contains different subsystems, and each subsystem has different energy state. So if the system is enough, of course you cannot make it, completely insulated, so the system will be in the thermal convection with the environment. We call it reservoir. So reservoir, and this is our system, and this is a universal system. So universal system, and we are talking about the equilibrium. So the situation is that this thermal convection between the system and the environment should be continued until the system reach a fixed temperature. So this thermal convection or transport will continue until the system reach state, we call it equilibrium, when the temperature of the system will be fixed at the T. So now my problem is that I want to know that what is the probability or chance for the system to be found at spatial energy here, or for example at temperature T. So there are two ways actually to find this probability. We call it PR. This will be like the number of the states which they have the energy ER. So we call it that NR. NR is the number of possibility. Always you need to remember the example I give you. Just 3 energy level and some particle. You want to distribute them. But we cannot make it that here because we are talking about more than 5 particles and then more than 3 energy levels. We have a huge number of the energy level and a very big number of the particles. Number of possibility at energy ER over the total, over total number, sigma NR. That will be like that. And because everything is averaged here, so we are looking for the average of the number of possibility at the energy ER over the total number of the particles. So if you can find that, this gives you the probability. Using the probability, you can find everything. For example, even this, for example, the N even, the N will be sigma NR ER. This is actually sigma number of the particle in each energy of particles at energy ER multiply the probability or the weight of them, probability or weight. Okay. There is a 2 strategy to find this PR. One is the hard one. One is using the counting method. So that's hard for me. Maybe for some people it's easy. So you have it like this 3 energy level and the 5 particles. Exactly. Energy 1, 2, 3, and you have the 5 particles. So 1, 2, 3, 4, 5, and you are going to distribute them to the inside of this. So you need just by counting by the hand. So if you have just 3 and if you have a 5 particle, you can distribute easily. You can get the exact number of them. Exact number. Exact number of the possibility. You did it this example before. But now we have more than that. We have more numbers. Still you can do that. Still you can say that the number of possibility will be something like opt n1 with energy E1, n2 with energy E2. I mean, put n1 number of the particle in this energy level, like for example 1 particle. Put 2 here and put, for example, 2 here. Again change, again change, again change. NR at energy ER out of total number. And total number is sigma NR, R from 1 to N. N1 to N. So it seems very logical to just start from the lower case and lower number and extend that to the. But I don't like that, so I don't like personally these methods. Actually, you can get the weight or the. You guess what will be here? Total number of particles will sit here, and n1 factorial, n2 factorial, and r factorial, and you can continue as much as you want. So that will be the weight of each state. But this is not independent because at the same time you needed to fix your energy. So it means that you're looking for the maximum of that, maximum at W and I, constraint to the condition. What is the condition? The total energy of the system should be constant. Okay. And one more condition is that sigma and R should be. So, you needed to remember this example. I just translated the example with more 3 energy level and more particles to the one which I know already. In our previous example, we had just 5 particles, so 5 particles needed to distribute over the 3 energy states, E1, E22, and E33. And in all ways, we needed to fix the total energy. For example, I told you that find the possibility for total energy 19, for example, 23, anything. Look at that. If you have more than one energy state, so in each energy state, you don't know how many particles will sit there. You have a different possibility. One possibility was that 1 particle here, for example, 2 particles here and 2 particles here, to get this energy. I don't check the numbers now. If you want 19, let's see what we can do. So what we can do is that, okay. Yeah, maybe we cannot, yes, maybe with this energy we cannot have it. So just change it and for energy, for example, for 30, give it some good number. Can I make it 30 as a total energy with number of the particle n, 5, and with the total energy state ER just 3 energy, or not? It depends. It depends that you can do that or no. So
the maximum number is 15.
Yeah, will be 15 or anything. I mean, if you fix E, so you can find the number of possibility. And by number of possibility, you can define the probability. This is the probability. Number of possibility over the total number. We have more than one energy state, as I write here, E1, E2, E8. And we have a more number of the particles. The total number of particles is n, and for each energy state, you are free to set few number of the particles. I mean, n1 can sit it here, or n2 can sit it here, or anything else. And I told you that this is like opt n1, n2, n3 out of the total number of n. So this will be the weight. So this will be the weight for each one. And you have this condition: the total energy should be constant, and the total number of particles should be constant. So, very quickly I will do these calculations because, okay, so if you remember the calculus, so it seems to me that I need to maximum or minimum, because why you want to go into maximum this great number? You know that if you have a more possibility, possibility, so in one sense your entropy will be the maximum, but from the other point you have a more option to get any energy with this more possibility. Well, one time we talked about, do you remember I asked you to plot for me this, you remember? I told you plot for me the E versus the, in that time we call it this omega. All the same, all the name of the same, omega. Later we call it G, density of the state. Now we call it derivative because we have more than one state, so it's not good to call it this E just anyhow. I ask you that to make it this. So if you make it that, you will see that always in any statistical system, that will be the peak. And in that peak, the omega will reach the maximum state. So the statement is that there is some maximum for that, for this function. But it's complicated because here you have just one variable, E. Huh? So when you take the derivative, you can just take the normal derivative, dE. Huh? Here you have more than one variable. So you have a multivariable real function. The value. This function is over from Rn to R. You remember this notation? Huh? It means that the input will be n number, so n1, n2, n3, n2, but finally you will get just one number. This is the value, the weight. So weight will be one number, and your input is the set of the n1, n2. So this function is multivariable. I want to tell you that. This function was single variable. Huh? Do you know why? Because here we just consider one system, and in ensemble we consider a lot of this, like that, a lot of that. So for each one you have a coordinate, so you have this kind of things. Anyway, you need to understand that we need to maximum that. If you maximum, you give more possibilities. For more possibility, you can handle the case, so you can have the maximum entropy for that. So how I do the maximum for this function? How I can do the maximum of that? And we have also the constraint here. The constraint are the total number of particles should be constant, and the total energy should remain the constant. So let's see. So this is the method. It's called Legend. Huh? We need to do the normal maximum minimum. How you find the externum? Tell me. You need to take the derivative of function, huh? And set it 0, and find the critical point. And just by checking the second derivative, you can see that this is maximum or minimum. We do the same here. But the problem is that this function is multivariable. So to know that this is maximum or minimum, you cannot just use the second derivative, the normal second derivative of the function. For example, x squared is the function with the minimum, huh? X squared. Because the second derivative of x squared is positive. Yes, at the point of this x0. But minus x squared is maximum, huh? Because exactly at the x0, at the same point, this second derivative negative. Huh? But here you have the function with more than one variable. So how you can know that this is the maximum or minimum? So that's need the multivariable calculus actually. But for the minute, we forget about all of this advanced mathematics. So we just treat this problem like the problem in calculus. So I wanted to find the maximum minimum of that. Because you have a factorial, so it's very unusual to take the normal derivative of that. I know that when W will be maximum, logarithm of W will be maximum also, huh? Because they are big numbers, so big function. So if this is maximum, so logarithm. But I really want to work with logarithm of that. Do you know why? Because logarithm of this G or omega or W is proportional to the entropy, huh? It's physical. So if you make this maximum, it means the entropy is maximum. And all the system in physics want to have the maximum entropy, huh? We several times told that. There is no proof for that. Nobody knows that why all the physical system want to get the maximum. This is the postulated, and we check that. When we see the array case of the decrease of the entropy in the nature, normally in some time in the cosmology. Anyway, logarithm the value ni will be logarithm n minus logarithm pi r1 to n and an r factorial. Can I write that? Yeah. And for each logarithm, I use the Stirling approximation. So it will be n ln minus 1 minus logarithm pi an will be sigma logarithm an. From here, we needed to write the approximation because I want to use also Stirling here. And r logarithm and r logarithm and r minus 1. Okay. This function should be maximum, but you have a two constraint also. The energy should be constant and sigma in r should be constant. So we use the method of the Legend method. Legend method is that you don't need it to take the maximum of that. You need it also to consider those functions. So the function should be maximum is this. n minus sigma r1 to n r minus 1n. You need to include them also here, this constant. Did you ever see this kind of method before? For example, you want, I will tell you, just let me to write that. So you needed to write, I don't know what is the better, just constant of the first first constraint, second constant. They are constant, but we will find them. What are they? If you do the maximum and minimum over this function, you will be sure that the solution which you find here also satisfies these conditions. Huh? Because maybe you find some maximum minimum for this, okay? But they are not able to satisfy these two equations. Huh? For example, you find Wn(i), for example, some maximum for some set of n by n, for example, n r minus 5. It can be maximum, give you a maximum to that. But with this condition, you can remove that. So I want to find the maximum and maximum of this function, but at the same time, I want to consider the constant. So this method is called a Legend method. So this is your function, so you need to do this maximum or minimum over here. If you do, you can find NR, and by NR you can find PR. So how you do that? You do as usual, you make it the variation of this function, differential. When you make the differential, this is the constant, because n is the total number of particles, is the constant. So you get here, minus sigma r1 to n. What is that? Logarithm differential of that. Delta NR, ln NR, minus 1, plus NR, delta NR over NR. Just make derivative, differential. Minus beta sigma ER, delta NR. Your variational parameter here is NR. Your parameter is NR, the one which you are looking for. You want to know that how many particles sit in which energy state. So this is NR. I cannot say the I cannot make this proof easier than what I'm writing here, because if you see in the textbook, it's more complicated than what I'm talking about now. Okay, just playing with that and make it more easier. So minus sigma r delta n r, I want to make factor from delta n r. Look at that, what we will have here. The logarithm minus 1 plus 1 minus beta plus beta er plus alpha. That should be 0, huh? This proof has a very high beauty, actually, because it seems that it's very much similar to define the equation of motion from the Lagrangian, huh?